Now we are going to be talking about principal component analysis. So before we go into the details, let's talk about where we are at in the process within the context of our CRISP-DM framework. So principal component analysis in the context of our discussion today is primarily going to be related to data preparation phase, where we are trying to reduce the dimensionality of our data and use the principal components as the predictors in our prediction problem. But you should also know that principal component analysis can actually be a form of unsupervised learning, where we're trying to understand the relationships and the correlation structures among the different variables. And so it's also a form of unsupervised learning. But again, in our context, we will be talking more about it from the context of data preparation and using it as predictors in our modeling projects. So let's talk about what makes an ideal set of data features. You want data features that have high variance. So features with a lot of variance contain a lot of potential signal and can be useful in our prediction problems. You want these features to also be uncorrelated. So features that are highly correlated with each other are less useful in certain cases and could be downright harmful in others. So for example, if we're looking at learning algorithms such as a multiple linear regression, as well as with discriminant analysis, they can be very harmful to the solution itself and bias the results. So having features that are uncorrelated is something that we want. You also do not want that many variables because we want to have a low number of features relative to our number of target variable observations. And a reason we want to have fewer features as possible is because of the curse of dimensionality. You may have not heard this term before, so I just want to spend some time and talk about it. So with this, what we're talking about is increasing the number of features is not always going to improve the classification accuracy. If we look at this chart here on the right, typically there is just a right number of predictors or dimensions to use that's going to give us the best performance. But the more you include, you will typically start seeing a deterioration of performance. So in practice, the inclusion of more features might actually lead to a worse performance and an increase in the risk of overfitting. The other thing is the number of training examples required increases exponentially with dimensionality. So it actually increases K to D. So K is the number of bins per feature and D is your dimensionality. If we look at this example on top, in this case we have one variable X and we have 3 bins. So we consider those to be categories. We have 3 categories in one dimension. And so this is what it looks like. So you can see here that the observations themselves are much closer to each other. Now when you go to 2 dimensions, it's a 3 by 2, so 3 categories, and then you've got 2 variables. You can see the variables start getting more separated from each other and sparser. Now if you go to 3, they're getting farther away from each other. So the higher the dimensionality of your data, it increases your risk of your data becoming sparse. Most train observations are going to be farther and farther away from each other the more variables you add to your model. This also means that new instances will likely be away from each other as well. And it is going to make it more difficult to predict and less reliable for our prediction to be when we try to predict new instances. So in short, the more or higher the dimensionality that we have within our data set, the greater risk that we overfit the model and the less reliable that our predictions are going to be. So one solution that we can have is we can remove or alleviate some of the curse of dimensionality by increasing the number of training observations in our data set, but sometimes that's not always feasible. So another option that we have is to use dimensionality reduction through things like principal component analysis, which is also referred to as PCA. And so that's another reason why we might want to do principal component analysis and use those principal components as predictors. So the big idea with PCA is that it can give us our ideal set of features, and it creates a set of principal components that are rank ordered by variance and uncorrelated, and we have a lower number. So it really hits on all of the things we just talked about in the last couple of slides that can be issues with our data features. Let's talk about the basic concepts. If two items are highly correlated, they may represent the same phenomenon, and they tell us about the same underlying variance and so combining them to form a single measure would be reasonable for two reasons. One, it's just parsimony. It makes it simpler. Fewer data features in our model is generally going to be better, and it also reduces the error in our predictions. So as we talked about before. So what does it mean when two items are highly correlated, or when features are highly correlated? So let's look at an example. Let's say we have 6 variables that we have collected. We have FICO score, number of defaults the customer has had, number of applications of credit they've had, their income, their assets, and whether or not they own a home. And so we have all of these variables. The underlying construct that we can derive from these may be that the first 3 may be speaking to your credit quality. So our first principal component may be credit quality, which is really comprised primarily of the first 3 variables of FICO, number of defaults, and number of applications. But you also have weak links between these other variables of income, assets, and own a home that are the dashed lines that we see here. The other principal component we may see here is debt capacity. So debt capacity may be based on income, assets, and whether or not they own a home. So from these 6 variables, perhaps we can reduce those 6 variables to have 2 principal components, one that looks at credit quality and one that looks at debt capacity. And then we use these 2 principal components now to then try to predict whatever our targeted value might be for our problem. The ultimate principal component analysis is dimension reduction method that creates new variables that are called principal components. PCA, performance spectrum, or eigenvalue decomposition of the correlation or covariance matrix of the predictor variables. So PCA creates components that consolidate more of the explained variance of the predictors into the first few principal components, and that's going to be accounting for anything more than any predictor in the original data set. So what does this actually look like? So if we go through this example, we see the principal components are going to be weighted averages by linear combinations of the predictor variables themselves. The first principal component is going to be made up of each of the different x variables that we had initially. And it's just the composition of those with different weightings. And similarly, each of the other principal components that we have will also be linear combinations. So the idea is that you can represent the correlation matrix within these variables using fewer principal components that still capture the majority or a lot of the variance that is embedded within the variables themselves. The other great thing about principal components is that they're going to be mutually orthogonal and that they're going to be mutually independent of each other. They're going to be generated so that the first principal component accounts for most of the variance in the predictors, so followed by the second component and so on. So ultimately you have 6 variables, but you will still have 6 principal components. But generally the first few principal components will capture the majority of the variability within the data, and therefore you'll just use the first few principal components as your predictive variables in your prediction problem. Really, the goal of PCA is to analyze the variance and reduce the number of observed variables. PCA reproduces the correlation matrix perfectly. The goal is to extract as much of the variance with the least amount of factors of principal components. So sometimes you'll hear factors being used interchangeably with principal components, and they're generally very similar to each other. And PCA will give us a unique solution. So let's talk about the method of PCA. It provides a unique solution so that the original data can be reconstructed from the results that you have. Using the principal components, you can actually recreate the x variables themselves. And it looks at the total variance among the variables that is unique as well as the common variance. In this method, the factor explaining the maximum variance is extracted first. So the first principal component can explain the majority of the variance. The second one explains the second most, and then so on. Let's visualize what's going on here. Here, each of the dots are observations that we have, and we're trying to do with principal component analysis is we're trying to find a new axis in the direction of the maximum variability that can be explained, and it's going to go through the centroid. So it's going to reference the middle, and this is going to be our strongest trend. So this line here explains that the most variability in our data set. And so the first principal component will be this particular line that will be formed here. And we're projecting that each of these observations onto this line. And that's how we're coming up with the first principal component. The second principal component is going to be the second axis, and it's going to go through the centroid and explain the second most amount of variance within the data itself. So what would be this particular line here? And you can see that these two lines are orthogonal from each other, and therefore they're uncorrelated to each other. And you can keep going at different dimensions. Obviously, it's going to be hard to visualize more than a couple of dimensions, but effectively you could have hundreds of dimensions that you're going through if you had hundreds of variables, and doing the same process and seeing which dimensions are explaining more of the variability. So these first two are the top two. Using these two principal components, we can capture a lot of the variability that we've seen in this particular data set. This is a visualization that we can use to visualize this. The blue dots are the original data that we have, and then the red dots that you're seeing are the projections onto the first principal component. You can see that it is finding a line that is going to explain the variability within the data set itself. And that would be this line that's being fitted. So the red line, the red dots are the projections of the data onto the principal component itself. And we can see this is then transformed from 2 dimensions down to 1 dimension. This is an example of an output that you could get in JMP. Notice the first component explains 86% of the total variance, and the second component explains 14%. So combined, these two components explain 100% of the variance. Within JMP, you would use the red triangle option to request the eigenvalue table. Note that this analysis was conducted on covariances instead of the default correlations. And this is one of the options within that red triangle drop-down menu. So let's just spend a few minutes. I'll just touch on this and explain what's going on. To do the feature extraction or the principal component extraction, we're doing a linear combination of different variables to extract a principal component. And this is particularly attractive because they're simpler to compute and analytically tractable. So given that you have an X that is an element within Rn, we can find the n times k matrix U such that we can project our experiments onto a new set of k number principal components. So we started with n number of observations, and we can try to explain as much of that variability in this data set using k principal components. So from a mathematical point of view, finding an optimum mapping is equivalent to optimizing an objective function, which computers are great at doing, and which is why it's a simple process to execute using a computer. I will post some optional slides that go through some of the mathematics. It's not pertinent for this class that we go through all the mathematics alone, but what is going on is thoroughly explained on those slides. And so those optional slides will walk you through the computations that's going on behind the scenes to extract those principal components. But what's important for you to understand is what is going on as far as what we're doing with the principal component extraction, and how we are using these to then predict and use them in our data mining problem. So we start with n number of x variables, and so that could be 100, let's just say. And we are projecting those 100 x variables onto an a k-dimensional space. And so then the k-dimensional space, or k principal components that we are going to extract, will be fewer than the n. In this case, I was using 100 as my example. So remember, 2 or 3 top principal components can explain the majority of the variability of these 100 X variables. So that is what we will use for our modeling. So some of the commonly used linear feature extraction methods are principal components, which is what we've been talking about in this lecture. And again, it seeks a projection that serves as much of the information and data as possible. So another type of extraction method, which we will talk about, is a classifier later on, is linear discriminant analysis. It seeks a projection that best discriminates the data. The principal components are dependent upon the units used to measure the original variables, as well as on the range of values that they assume. So because of that, data should always be normalized prior to using principal component analysis. Typically when you're using a software such as JMP, it will automatically do that for you. But if you're using other software packages, you need to make sure that it doesn't, whether it does it for you or not. So sometimes you'll have to do the normalization prior to conducting your principal component analysis. So let's spend a couple of minutes and just talk about what's going on. And again, as I mentioned earlier, I'm just touching on these and the mathematics behind the scenes. So that's all going to be in the supplemental slides that are posted in the course. But in those slides, I've included some additional information that will walk it through in more detail, and you should you want to go through that level of detail. So in this case, we're again creating a combination of X variables to extract a lower number of factors or principal components that we're going to explain the majority of the variance that we are seeing. And in this case, here we have all these X variables that we're looking at. And what we're trying to do with PCA is going to seek to represent the X and the new space of lower dimensionality using K basis factor. So we have, again, instead of using 100 variables, 100 X variables, we can have fewer K principal components that explain much of the variability that we're seeing within our data. And so what we're trying to do here is we're trying to find an X hat such that the absolute value of X minus X hat is minimized. And so you're minimizing the information loss with fewer number of principal components. The other thing which I mentioned at the beginning of the discussion is that the principal component analysis can also be used as an unsupervised learning method. And typically when you're doing unsupervised learning, you want to interpret the results. And one of the things that's interesting or that needs to be considered when using principal component analysis as an unsupervised learning method is that we oftentimes need to rotate the vectors that we extract to make the data more interpretable. So let's talk about rotation factors that can be employed to make your data and the principal components more interpretable. You rotate your factors to maximize the high item loadings and minimize your low item loadings. This will produce a more interpretable and simplified solution. So the way I think about it is, as I mentioned before, each of these X variables, so let's say we add 100 X variables, we're going to take each of those 100 variables and they're going to load to some extent onto our different principal components. By rotating the factors or principal components, what we can do is maximize the loadings for the ones that have high loadings and minimize the ones that have low loadings. So it makes the overall principal components more interpretable. Two common rotation techniques are orthogonal rotation and oblique rotation. Oblique rotation, the data themselves underlying it is highly correlated, or the factors may have some level of correlation. And if they're completely orthogonal, there's no correlation at all. You typically can just use the Varimax rotation, which is an orthogonal rotation. So let's talk about how to choose a number of principal components. Again, the goal is to have the smallest number of principal components accounting for a significant amount of the variation in the original variables that we selected. You typically want to retain as many components so that maybe 70 to 90% of the total variation is explained. So this is just a heuristic or problem-solving approach. There is not a specific rule that says you need to have a specific number of principal components. So typically you would be applying some sort of heuristic to decide 1 is the percentage of the variation being explained, and oftentimes 70 to 90% is typical, using as a reasonable number. There's also the Kaiser criterion. So some statisticians whose last name was Kaiser came up with this, and the idea is that eigenvalues greater than or equal to 1 tend to be a good heuristic to use. Another very commonly used one to look at is a screw diagram. So what a screw diagram looks at is the number of principal components corresponding to an elbow. So when we're talking about the elbow, we're talking about this spot right over here, this bend. So you have the component number. Let's say we had 12 variables, and the 12 components on the x-axis. You have the eigenvalues for each of these components here on the left, and you examine the scree plot. It's going to provide a visual of the total variance that is associated with each factor. The first one has the highest eigenvalue. A higher eigenvalue means it explains more of the variance. Then you see the second one explain the second most variance, and you can see the steep slope shows that the large factors at the beginning, and then they kind of start to taper off. So this gradual tailing off that shows the rest of the factors lower than eigenvalue 1 here. And so that's the dashed line that's shown. Typically, one heuristic you could apply is to select the number of factors or principal components where the elbow is forming. You can see here that the elbow is forming at 3 principal components in this case. So you would use 3, which happens to also align with the Kaiser criterion. Again, the Kaiser criterion says to select those with eigenvalues of 1 or higher, which also means that you would take the first, second, and third principal components. So just a couple of comments here on principal component analysis. PCA simply performs a coordinate rotation that aligns a transformed axis with the direction of maximum variance. As we saw in some of the earlier visuals, a new covariance matrix is diagonal. So what this means is that it's going to be producing a new set of variables that are completely uncorrelated to each other. And again, the first few account for the majority of the variance, so we can select a number of components there for reducing the dimensionality of the data. Then we can also remove the multiple collinearity because each of them are orthogonal to each other and therefore are going to be uncorrelated with each other. So let's talk about the pros and cons here. The pros are that it reduces dimensionality, which again is one of the intents. It's interpretable, meaning that each of its principal components, you can see the loadings and what is contributing towards the principal component. So as we saw earlier in the very first visual, we talked about how one of them was credit quality in the first few variables. And then we looked at the loadings. We could decipher what variables are loading to that first one. And credit quality is not the name that's going to come out from your output. As you know, I just gave you a principal component 1 in the loadings. In looking at the loadings, you then decipher what that particular principal component meaning is. So you, again, you could name it something else, but in this example, we named it credit quality. The second one we named debt capacity. And so that's the name that we gave the component. All the variables will tell you here is that the loadings by variables to each principal component, and then you have to interpret what that means. And so as we mentioned earlier, you can create a principal component very fast and it runs very quickly, which makes it very easy to implement. But one of the downsides of it is that it's incapable of learning nonlinear feature representations. So if your data are not linearly related some way, then principal component analysis may not be the best choice for your particular project.